let C be a circle with diameter d, and let L be a horizontal line that's tangent to the circle. Now let's add another circle here so that it's touching both the line and the bigger circle. It doesn't matter what the size of this new circle is, so long as it's smaller than the original one. We'll call this new circle C0, which will have some diameter D0. If we zoom into this enclosed little space, notice that we can fit another circle in here, with it also touching both C and L, along with C0 this time. If we'd like, we could keep adding more circles in this way, and in fact, we can fit an infinite amount of them, which becomes easy to see the more we zoom in. Now, let's label each of these newly added circles starting with C1 and pluck out any one of them at random, which we'll call C sub k, where k is some integer greater than 0. The task is to find a formula for the diameter of C sub k, in terms of both the diameter of C0 and the diameter of the original circle C. So how should we go about solving this problem? Here's your chance to pause the video if you'd like to give it a go before we go through it together. Alright, let's start off by isolating an arbitrary circle along this path, aside from the first one. This will be our C sub k. Our goal is to come up with a formula for the diameter of this circle, using only the diameters of the original circle C and the first circle along this path, C0. So essentially what we're trying to figure out for this problem is how any given circle shrinks the more it squeezes between a larger circle and a straight line. To make it easier for us, let's first consider two consecutive circles, with the second circle here being the one preceding C sub k, which we'll call C sub k minus 1. Once we figure out a relationship between the diameters of these two circles, it won't be too difficult to generalize it for C0. Now, before we do anything else, it's always a good idea with geometry problems to draw some lines and/or points to help guide us in the right direction. So let's begin by drawing some origin points. Also, let P sub k, and P sub k minus 1 be the points of contact between the line L and our three circles. Now, let's draw a line connecting the origins of C and C sub k minus 1 and create a right triangle with it that starts at a point which we'll call A. Using our trusty Pythagorean theorem, we can acquire the following equation. This doesn't look like anything special, but we can rewrite it to be more useful. For example, notice that the hypotenuse of this triangle is just the radius of C added to the radius of C sub k minus 1, while the vertical line OA is just the radius of C minus the radius of C sub k minus 1. And finally, the line that makes up the base of the triangle has the same length as the line connecting the points P and P sub k minus 1. Now, lucky for us, this equation actually simplifies pretty nicely. And on top of that, we can run the exact same procedure for a line connecting the origins of the circles C and C sub k, which will give us a similar equation to work with. Now, at first glance, these equations may not seem all that useful either, but they will come in handy later on, so let's just keep them in our back pocket for now. Let's keep going and draw another line, connecting the origins of C sub k and C sub k minus 1 this time. We can create and examine another right triangle now that meets at a point which we'll call M. Using the Pythagorean theorem again, we can acquire the following equation, which we can again try to rewrite to serve us better. For example, notice that the line connecting the two origins is just the radius of C sub k minus 1 added to the radius of C sub k, while the vertical line here is just the radius of C sub k minus 1 minus the radius of C sub k. And lastly, the horizontal line here has the same length as the line connecting P sub k to P sub k minus 1. Now let's rearrange what we have so that the diameters are all on one side. And would you look at that, things simplify quite nicely for us again. Now, we've got three different equations to work with, but we still can't make any useful substitutions between any of them. So let's go ahead and fix that by changing one small detail. And that's rewriting the line P sub k minus 1 as P sub k minus 1 minus P sub k, and then taking the positive square root on both sides, which we're allowed to do since the line P sub k is clearly shorter than P sub k minus 1. Alright, great, we can now use the first two equations and substitute them into the third one to yield the following, which consists of nothing but diameters, which is exactly what we want. After dividing both sides by the square root of d sub k minus 1 d sub k, and with a bit of simplifying, we get the following equation. And we're in luck here, because this equation actually lays the foundation for the generalized version as well. And after a bit more manipulating and simplifying, we can finally get what we're looking for, a formula for the diameter of any circle along our infinite path, in terms of the diameter of the initial circle along the path, C0, and the diameter of the larger circle, C. Alright then, here's my question to you. What if instead of drawing circles successively to the left of some initial circle C0, we drew them successively to the right? Can you find the formula for the diameter of any arbitrary circle along this path, again in terms of the diameter of C0 and the diameter of C? This would work out very similarly to the original problem. So for some additional spice, use the equation you derived to also determine how many circles can be drawn in this way before the construction is no longer possible. Meaning, how many circles will we be able to add before the next circle can no longer touch both the line L and the circle C? So, what do you think? Leave your thoughts in the comments below, and if you enjoyed the video, please don't forget to leave a like, it really helps the channel out a lot. And while you're at it, subscribe for the many more math problems and puzzles coming very soon.